Okay, good evening. Welcome to the third online learning session for A1 Chemistry. Today's session will be again delivered by Mrs. Stevens, as you know, an examiner for the WJEC. In today's session, you will be reviewing enthalpy changes. My name is Mr. Black, and I'm going to be available in the chat for you. If you've got any questions, please do ask, and I'll do my best to answer them for you. So I'll pass you over to Mrs. Stevens.
Good evening, Year 12. So I'm going to try just covering something that was touched upon definitely in GCSE, but probably a bit more disguised than it should have been, certainly talking from my own experience. But it does tie in with the very first session I did with you 2 weeks ago, which is that session we did on Le Chatelier and how enthalpy of a reaction impacts quite heavily on an industrial process and the conditions that they choose in it. So it kind of ties in nicely with that one. So marries that, if you marry that knowledge of what we did 2 weeks ago with the knowledge from here, and they are in two distinct units, aren't they? So the Le Chatelier's principle, equilibrium, was very much in unit 1, and this is in unit 2. But as is the case in lots of AES chemistry, they cross over so frequently and so effortlessly. If you've understood all the components, then it shouldn't be too much of an issue for you. Okay, so going back to basics really, because I'm understanding that probably across the Wales you've got people at different points. So if I go back to GCSE, and we didn't really use enthalpy massively, you might have used like the heat of a reaction or the energy given out or taken in within a reaction. So if you think back to GCSE, we know that when a chemical reaction is taking place, that is often accompanied by heat being taken in or given out. Okay, so there are distinct terms that you have to be familiar with this. So if you remember, the word we use when heat is given out is exothermic, and that second statement there where it says what's the word when heat is taken in, it's classified as endothermic. So I often get my kids to just look at the door when I'm teaching this and say, like, if you come in, you are entering, and when you are leaving, you are exiting. So they get this sort of sense of whether an energy is taken into the system because energy is required in order to facilitate that reaction, or whether energy is given out because there's surplus energy already within that system that then results in it being given out to the surrounding area. Okay, so for GCSE, you came across these sorts of diagrams that represented these energy changes. So you've got endothermic and exothermic, but which one's which? Well, it's all about thinking, right? If energy is being given out, does that mean that the products possess less or more energy than the reagents in which this product was created from? Okay, so if you think about it, in the first diagram here, you can clearly see that the energy at the beginning is much, much lower on the y-axis than it is on the at the end, so the products. So that represents, therefore, that heat must somehow have been injected into that system in order for the products to possess more than it had to begin with. So the reactants have a certain amount of energy, and then the products have a different type or amount of energy. And in order, you can see there, simply by the fact that the y-axis has moved upwards, energy must have been taken in. So the opposite must be true for the other side of that page there, you can see. So reactants had a set amount of energy there, and the products possessed less. Okay, so if you start with this amount of energy up here, okay, and somehow you've resulted in having a product that has less energy within itself than you started with, then where's that energy gone? Well, that energy must have been given out into that environment or the surrounding area, and heat is therefore given out. So to be clear, this is a representation of an endothermic, okay, reaction. So you've got endo. That is really untidy writing. It's been a very long week as well. So if I just make that slightly tidier for you, apologies. So you've got exo and endo, okay, but I'm now going for the highlighter. So you've got endo and you've got exo, and being the classic scientist than I am. I'm always a bit lazy and I just go for the beginnings, so exo and endo. So it's all about getting your head around whether you possess more or less energy at the beginning or the end. And that difference, whatever it may be, has to then be accounted for, and whether the environment has supplied that energy, so energy gone into it, or whether the surrounding area has received that energy in the sense of an exothermic reaction. So as all chemistry, I'm sure you've come to this conclusion yourself by now. It's got its roots in languages we don't particularly use frequently anymore. So the definition enthalpy has its roots very much in the Greek language. Okay, so it's to do with the two words that combined together to give some sense of the definition that's been developed since the early 20th century. So enthalpy. So you could go around and you could give a really complex definition by all means. Okay, so that's quite a long-winded one. What is important, as I hopefully have got across to you in my earlier session, is that there is no such thing as a perfect definition. The definition has to be something that you are comfortable with, that you are able to produce under exam conditions as required, but at least the core meaning of it is going to be the same. It doesn't matter if your friend William has got a definition or your friend Mary's got another one. As long as you are saying the same actual at its core principle, then it doesn't matter how you say it. So get your own personal definition. Okay, that is really important. And as a consequence, and there will be questions, and the past paper questions I've got at the end of this PowerPoint give an example of such a question. They will say define, but don't get scared by them. Just fall into your comfort zone of knowing what you know and put down in your own words what you're trying to say. Right, so thermodynamics, as is the case with lots of science, okay, we go over it so many times, you can't create nor destroy anything. It's the same, it's the principle of why balancing equations is important in chemistry, isn't it? Okay, so you know you can't create nor destroy any atoms, they just get dismantled, rearranged, and rejigged into new form. Well, the same thing is true for energy. The first law of thermodynamics is that energy can't be created nor destroyed, okay? But it can very easily and very frequently be converted from one form into another, okay? So energy changes, all chemical reactions are accompanied by some form of energy change. Some are really obvious, smack in your face obvious, and some are a bit more discreet and can potentially therefore go unnoticed, but that doesn't mean that those changes aren't taking place. So you've got exothermic, as I said in the earlier slide, energy is given out. So the system in this transition from reactants to products ends up having an excess of energy that is therefore given out into the environment or to the surrounding area. And you've got the exact opposite then potentially of endothermic reactions, that energy is therefore absorbed. And it's absorbed because in order to facilitate that change from reactants to products, that system requires an injection or an input of energy. Okay. I'm fully aware that, and it doesn't matter how many times I go over it as a teacher, and I'm knocking on the years now. So every year I still struggle to get everybody to accept that if something's getting colder, that it's absorbed energy. It's like, well, it's got colder, miss. Surely if it's got colder, it's not absorbed energy, because absorbing energy would make it hotter. It's not, okay? You have to be clear that these changes in energy is to or from the surrounding area. So if the reaction is in aqueous solution, okay, and it's gone out into that aqueous kind of phase, i.e. the water, then that water will heat up if it's giving out energy. Okay, but in the same sense, that water has to supply the energy for endothermic reactions. So do not let that throw you in the panic of an exam that you think something getting colder, oh, has it absorbed or has it given out energy? Well, just be clear. Exo, energy is given out. It will generally be seen as something getting hotter, and endothermic energy is taken into the system, but as a result, the surrounding area gets colder. Okay, so exothermic combustion is the obvious one, and we will deal with specific definitions of enthalpy of combustion tonight. So we know that burning anything will always be exothermic. Okay, that is also something to keep in the back of your mind. If it's combustion, if you're burning something and you somehow end up with an enthalpy that is positive, bad news, you've gone wrong somewhere. Okay, because the values that we will work through as part of this session, the core principle is that the enthalpy, which is represented by a symbol called delta H. Okay, so the enthalpy tends to be in an exothermic reaction very much negative. It's always been negative. That's what represents exothermicity. Okay, but if it's negative, it's exothermic. If the calculations or the enthalpy change recorded and calculated by yourself comes out to be positive, then you can deem it to be an endothermic reaction. So delta H, which we'll come to in a second, minus or negative is an exothermic, endothermic is a positive value. Okay, so I'm sure if you go back to what, key stage 3 word equations, you will always taught, or were, I hopefully always taught, the respiration is glucose and oxygen giving way to carbon dioxide, water, plus energy. Okay, I've just literally done it with my own year 9 where I put these kind of big bubble around plus energy, because respiration, and the purpose of respiration is to release the energy from the food you eat in order to facilitate the function of the human body. Okay, so respiration, we know, is an exothermic reaction. It is designed to give out energy. The exact opposite then can be said for photosynthesis. Photosynthesis actually requires energy, and the way you recall that from kind of a bit of, not common sense, but yet from everyday reference, is it requires some, sorry, give me a minute. That was the people trying to make sure I wasn't locked into the building tonight. So I was saying, endothermicity, photosynthesis, you have to require, you have to have sunlight. Yeah. So thermal, if you've come from a background of triple award, then in year 10 you'd have also done that unit on limestone, which takes into consideration the thermal decomposition of calcium carbonate. Okay. So there are common examples of exothermic reactions and endothermic reactions that you've picked up either in GCSE or before possibly, but certainly throughout year 12, you'd have picked up further examples that you should be able to kind of call upon quickly and effectively. Right, so enthalpy changes. It's a measure of heat content of a substance at a constant pressure. You cannot measure the actual enthalpy of a substance. You can measure an enthalpy change, however. So it's written, as I already said verbally, as the symbol triangle, delta H. So the enthalpy change of any reaction is the enthalpy of the products, take away the enthalpy of those reactants. Okay. So those are the classic energy diagrams for the exothermic reaction. So you start off at a certain amount of energy, and you then fall down to a lower state of energy, the difference of which is therefore given out into the environment. Now, in energy diagrams, there are clearly two things that you have to be able to label confidently. And in both cases, the two things that you have to be able to label is delta H itself, okay? And also, you have to be able to label the activation energy. So if you go back to your year, I think it's year 10, isn't it, the rates of reactions, and certainly depending on where you are in your year 12 units and topics currently, you do rates of reactions. Okay, so if you think about the definition of activation energy, it is the minimum amount of energy that's required to facilitate or to allow a reaction to proceed. Okay, so it's the minimum, the very bare minimum energy. So if you look at an energy diagram like so, the two things would be, I keep telling my pupils myself, it's that kind of hill to climb, isn't it? It's that minimum amount of energy that's required just to get it started. Now, don't get me wrong, in an exothermic reaction, there will be energy given out to the environment, okay? But that is also the case for that initial bit. You have to input some energy in order to get the payback later on, okay? So it doesn't matter how downhill it is on the other side of that hill, it's like riding a bike. If you want to get to a village and there's a little hill, you're going to have to get up that hill before you get that kind of payback of rushing down that hill on the other side. Okay, once you've started though, then the energy supplied by your own reactivity will then be enough to keep it going. Okay, but that doesn't take away the fact that you have to have that initial injection of energy. Okay, so the E activation energy will always be present. Every reaction has a minimum amount of energy required. Okay, so you have to be able to label as there. You can see in the kind of purple blue line, that's the activation energy. The delta H, or the enthalpy of any reaction, though, is always going to be that distance between the beginning and the end. So you can clearly see that reactants were up here, products were down here. So that, therefore, as already labelled for you, is going to be the delta H, or the enthalpy change. Okay, and as I said earlier, it's always going to be negative for an exothermic reaction. Okay, if you go to the endothermic, though, you've still got to climb that hill. The difference being that this hill is a lot more substantial because the payback you get afterwards is much less. Okay, and for that reason, you have to continuously supply it with energy in order for it to continue. So same thing though, activation energy is wherever you start from, okay, to the very peak or top of that hill. So if you go back to the slide before, can you see? You start with where you go from, and you make your way to the top of that peak. That is activation energy. In the case of an endothermic, though, that hill is quite substantial. You can see that it has to go all the way. Yet again, though, there hasn't been a massive change in the rule of how to label it. Where you start from to the very top of that hill. So we go all the way to the top of the hill, and that is activation energy. To classify the reaction, or to repeat them what I said earlier, the enthalpy, though, is always going to be that distance between where you start from and where you end up with. So in the case of an exothermic, you start high and you end up low, but it's still the difference between them. If you kind of align them, it's the gap between them. And the same sense, in an endothermic, you start low and end up high. You're still looking at, if you align them on top of each other, that gap between where you start and where you end. That is the enthalpy change of any system. So even though I can appreciate that as the reaction proceeds, that it's a bit difficult to maybe visualize where you start, which is here, and where you end up. But if you visualize them lined up, it's maybe easier to get your head around that that is actually going to be delta H. So think about the beginning and the end aligned on top of each other. Okay. All right, so standard enthalpy changes. Standard is a key thing. Now, it happens in most of Unit 1 where you have to be able to regurgitate what is meant by standard conditions. So you've got the pressure of 1 atmosphere or 100 kilopascals, and the temperature is in a scale called Kelvin, as I'm sure you're familiar with manipulation of things like gas laws and stuff by now. Temperature is in Kelvin, which is equal to 25 degrees C. But for calculations, it is stated as 298 Kelvin. Okay. So as a guide, just think of how a substance would be under normal lab conditions. Assign the correct subscript then, so make sure that you're clear in standard form. Is it likely to be a gas, a liquid, or a solid, to indicate what state it is. If you have a solution, then it's important that you are clear that it has to be at a concentration of 1 molar. And if the standard conditions are used, we modify the symbol to delta H, therefore. Okay, so we use this symbol here. That signifies standard conditions have been accounted for. Okay, so you've got standard enthalpy of formation. So formation, pretty self-explanatory, I hope to you, is that the enthalpy change, therefore, to create or form 1 mole of a compound. Yet again, we're going back to standardization here. So 1 mole. So the enthalpy change when 1 mole of a compound is formed in its standard state from its elements in their standard states. And that's crucial, okay, because often enthalpy of formation takes into consideration gases like oxygen. So as long as the elements that you're creating it from are in their standard states, then the symbol and the enthalpy we're dealing with is this one here. So delta HF, so the enthalpy of formation. Usually, but not exclusively, but I would say nearly always that standard enthalpy of formation is an exothermic process. Okay, so graphite, carbon, if given, is usually assumed to be the graphite allotrope form of itself. So in these type of enthalpy calculations, it's hardly ever referred to as you're not meant to assume that it's diamond, you assume that it's the graphite allotrope that's present. So graphite in the form of, carbon in the form of graphite will oxidize with oxygen to produce carbon dioxide gas. In the same sense, hydrogen will oxidize in a good supply of oxygen to form water. Okay. You can then combine these, so you can take carbon and oxygen and hydrogen and combine them to make ethanol. Okay, so as long as you have the kind of atoms that are required to form the compound at the end, it is you're able to calculate that using then standard enthalpy of formation as a basis of your calculation. So 1 mole of product on the right hand side of the equation. Okay, elements in the standard states have 0 enthalpy of formation. So carbon is usually taken as the graphite allotrope as well. So these are just a few notes for you just to take into consideration, because it's going to be true throughout the enthalpy unit. Okay. To aid balancing, as always, you have to stick by the fact that you can't create nor destroy things. So to aid or to make balancing much easier, remember that to get 1 carbon dioxide molecule for every carbon atom in the original, okay? So you need, in the same sense, 1 mole of hydrogen to make 1 mole of, 1 mole of water is created from 2 hydrogen atoms, okay? But hydrogen is a diatomic form of itself, so be careful that you're balancing this, okay? So don't trip up in thinking that there is the same number of atoms as molecules sometimes because of the diatomic nature of most gases, okay? Always leave the oxygen to the very end. Okay, don't start fiddling with the oxygen. Oxygen is the very last one you will try to balance within most equations. Right, enthalpy of neutralization. Now, neutralization is something that is explored quite vastly in GCSE. Okay, so it's neutralization as a kind of byproduct will create a salt always. Okay, so the enthalpy change of 1 mole of water is from its ions in dilute solution. So you should have picked up by now that the definition of an acid is a proton donor and the definition of a base is a proton acceptor. Okay, neutralization is always an exothermic process. So to simplify it, in an acid form, you've got the protons. You've got the alkali most of the time. So in basic form, you've got something that's capable of accepting that proton to create, as a result of neutralization, water. Okay. A value of, not that you're meant to remember it, so don't get panicked, okay? But you will get a value of around -57 kilojoules, which shows that it's exothermic because it's negative, is obtained when strong acids react with strong alkalis. So things like HCl and HCl and NaOH to make water and NaCl. Okay. Now then in GCSE you also did this and it hasn't changed. The only thing I would emphasize here is that you need to stick to the basics you learned in GCSEs, which is look at the bonds you're making and look at the bonds you're breaking or making, and then make sure that you account for every single one. So for example, there you can see that chlorine, okay, makes 2 chlorine atoms. So that's the strength of the bond. So the energy needed to break a bond is exactly the same as the energy required to reform it. Okay, so the bond energy or the bond enthalpy is the same whether it's being broken or made. That's very, very central to how these calculations work. Okay. So I'm sure you're familiar from GCSE, you'd be given these values. You are not expected to know any of these values off by heart, I'm glad to say, because I don't remember most of them. So as long as you know what bonds are present in the reagents and you can see what bonds are present in the products, you should be able to then apply what I teach my kids, and it's not a bad rule, I suppose, is break, take away, make. So work out how much energy is needed to break all the reactants into their constituent atoms, and then work out how much energy would be released when you remake or create the new products. So the rule is break, take away, make. Okay, given supplied data such as this. So if you're told what the bonds values are, it's just a case of mathematically working out what you have at the beginning, working out what you have at the end, and then just working out the mathematical difference between them. For somebody like me who loves maths, and a lot of my year 12 currently quite enjoy the mathematical element of it, this isn't too bad at all, because it is literally number crunching. Okay, which takes me to the crucial thing here, which is Hess's law. Now, Hess's law states that it doesn't matter how you get from A to B, you can do it with a halfway house in between, or you can do it in one fell swoop directly. Hess's law states that it doesn't matter what path you take, the enthalpy change to get there will be the same. So the enthalpy change is independent of the route or path taken. So for example, you could take, I suppose, carbon, and we know that carbon in insufficient amount of oxygen will create carbon monoxide, okay? But then if you supply carbon monoxide with further oxygen, it will create the probable product of CO2. However, you can create carbon dioxide directly from carbon. So the energy for going directly, if I label them, actually I should have labeled them slightly different then. Doesn't really matter, you'll get the gist of it, okay? If you go directly from C to CO2, it is equal to that value B. However, you could have worked it out by initially going to CO and then further oxidizing that CO into CO2. So it could be a direct route, it could be an indirect route. So there is that example there for you. It's easier probably to get your head around this principle using generic symbols like A, B, C, etc. Okay, so if I take you through the example, just to show you, it can be three-sided triangle and tends to be in year 12. They keep it relatively simplistic that it is a triangle. So this route, or you can go via one intermediate and then go to the final product. In year 13, anybody that's carrying on, I won't kind of scare you overly, but it gets a lot more complex in year 13 when we start expanding it into what we call a Born-Haber cycle, where as a consequence of the paths taken, there are multiple steps in order to get your head around, okay? So Hess's law for year 12, though, relatively simple. Work out the enthalpy or the energy for one route, and then work out the energy for another route, and the difference between them must be the unknown value. So you'll often hear, I hope, your teacher saying the rule that clockwise arrows are equal to the anti-clockwise. So as long as you, for example, if I knew that and I knew that, okay, if you think about the motion, the direction of those arrows, you could theoretically, mathematically work out that third unknown value, because the rule that the total of all the clockwise arrows would numerically be equal to all the anti-clockwise arrows. So clockwise is equal to anti-clockwise is in any Hess's law cycle interpretation, okay? So Hess's law, applying Hess's law enables you to calculate things that possibly you might not be able to calculate experimentally, shall we say. So it allows you to use data such as things you can't measure directly, like lattice enthalpy, enthalpy changes of reaction from bound enthalpies, enthalpy change of reaction, so if you burn something, or enthalpy change of formation. So you can use other supplied information in order to work out a route or a path that doesn't have to be undertaken itself. So it's a way of kind of getting a sense of a reaction without actually carrying out that reaction itself. So enthalpy of reaction from bond enthalpies. So the theory here is that if you have a reaction, you think about all the reactant species or the atoms being broken up and shattered into these individual atoms, okay? But then you reform them and put them back together in their product side, okay? So the overall energy change depends on that mathematical difference between the energy required to break them and the energy then released when you make a new bond, because that's the theory. To break up a bond, you need to input energy. When you when you form a bond, it is an exotherm, or gives out energy. So it's all to do with mathematically working out, do I need more energy to break all the bonds that I would get by repaying, by making the product, or do I need to input less energy to break up the reactant particles, comparable to how much energy I'd get paid back later on by remaking new bonds in the form of the product? So it's this balance of looking at, what do I need most for? Do I get enough energy back by remaking the products? And if so, it's exothermic. Or do I not quite have enough energy repaid when new bonds are made, making it an endothermic reaction? Okay. So enthalpy of reaction from bond enthalpies then. An alternative view, or an alternative way of getting your head around it then, which is probably closer to the Hess's law one I was referring to, okay? So this cycle of clockwise versus anti-clockwise. First step, work out the energy to break all the bonds, to separate them into the gaseous atoms, okay? Step 2, gaseous atoms then combined form the bonds and energy is then released. As the value should be equal and opposite to that. And this is really important that you appreciate this. The energy for breaking a bond and making it is the same. Okay, the values aren't any different. So because in step 2, the root of us going in the opposite direction, and this is where the clockwise and anti-clockwise element of what I was saying come into place, its value is therefore subtracted. So the delta H here, okay, is equal to the enthalpy of the reactants, take away the bond enthalpies of all the products, okay? But they'd have to account for the negative value of giving out an energy comparable to taking it in. So it says there, calculate the enthalpy change of the hydrogenation of ethene. You'd not expect it to remember the values, thankfully, of any bond. But if I tell you, or let's assume that these enthalpies would be supplied to you, the bond energies, you can see, okay, that and I usually tell my pupils, even in year 13 and onwards, okay, to break it into the before and after, okay? So we're only concerned initially with this side, so you can pretty much ignore that side for a while, okay, and think, what energy do I need to do to break everything going? So you can see, I need to break acetyl 1C, and I even tell them to slash them. So right, that's it. I need to break 4 CH bonds. So I've got to break that one, that one, that one, and that one. So you can physically, or visually then, shall I say, see that you've accounted for it. So you don't risk missing anything out. So I've done that. And then you can see that I actually need to slash that one as well. So HH. So physically doing it, and there's no rules to say that you can't do it as an examiner. They can't object to you scribbling on the diagram and slashing bonds as you go along. In fact, I usually go, that teacher's told them to do it, and it's good practice, okay? So that's one side. So you've got the before, should we say? And then it takes you to the after. So now we're concerned with the other side, which is this one, isn't it? So ignore that side for now and focus on this one. So what new bonds are we going to make? Well, you can see that you're making a single bond between the C and C. And I'm fully aware that you're not slashing or breaking them. But by continuing this practice of slashing them in the diagram, then you know you've accounted for it at least. Okay, so I've formed a bond between a CC, happy days. I also need to form 6 bonds between a C and a H. So 1, 2, 3, 4, 5, 6. Okay, and then mathematically work out that. So yet again, this type of data would have to be supplied. So you mathematically work out how much energy you needed to input to break everything apart into its atoms. You then work out how much energy is released when you take those single atoms and bung them together into the product. Okay, so applying Hess's law, therefore, so the break and then the make, then it works out to mathematically be this value here. Okay, so it is taking the values that you've calculated here. So as I said, it is break, take away, make. And that's usually what I teach from year 11 onwards, is that it literally is B, take away M, break, take away, make. Okay. Right, enthalpy reaction of formation. If you form the products from their elements, you should need the same amounts of every substance as if you form the reactants from their elements, because of the fact that you can't create something from something that wasn't there in the first place. So as I mentioned earlier on in the session, enthalpy formation tends to be exothermic. So you've got the same steps as I followed earlier. I won't dwell on them too much, okay? But it's a case of getting your head around the clockwise versus the anti-clockwise concept. So if you think of this as a cycle, okay, then you can see that that arrow is going clockwise, isn't it? But this is going anti-clockwise and anti-clockwise. So the two whole cycles, so clockwise direction and the anti-clockwise directions, have to be equal. Okay. Right. So if they give you, or they supply you with data such as the following, then the sample calculation, calculate the standard enthalpy of change for the following reaction, given that the standard enthalpies formation of water, nitrogen dioxide and nitric acid are as follows, or as those values respectively, then you simply have to apply this. Okay, so you work out how much is needed to form all the products, you subtract how much energy would have been required to form them as the reactants initially, okay, because you assume that you're creating the reactants out of their atoms before you then take those and turn them into the products. Okay, so how much energy is needed to make the products, account for the fact that you'd have to initially supply some energy to create the reactants from their constituent atoms. So it is products, take away reactants, and an example there shows you that it would give you an eventual answer as so, which is exothermic, denoted by the fact that it's a negative number. Okay, so there are lots and lots of examples. Okay, I've supplied more than enough and probably far too much, but I figured when you are trying to get your head around this independently and you watch the sessions back, etc., and you can pause, then the more questions there are for you just to get your head around and practice, the better it will be. So there are lots. Okay. Mathematically, you actually have to also be able to recall this equation there. Okay, I'm hoping that your teachers have either taught it already to you or you're familiar with it. My year 12, for example, are quite frequently told about MCATs. Okay, so it's the formula as I was taught. So it's a way of recalling the mass multiplied by the heat capacity within a system, multiplied by the temperature change that occurs within a system. Okay, so I'm fully aware that it is coming up to the end of the session and I've talked far too slowly potentially, and I was hoping to have got into this measuring of enthalpies much more. But as every session, be it myself or Mr. Black, the information is there for you to kind of mull over in your own time. So by the end of this PowerPoint that you'll be sent, okay, there are lots of past paper questions as well. So for example, this was the first one that asks you, standard question, which letter represents activation energy, which number represents the enthalpy change, etc. So, and after each, and I suggest if you watch this at home that you have the sense to do this, don't fool yourself by just going straight to the answer. The answer will follow, I promise. Okay. For example, you can see the answer is A. Look at the question, pause it, think, do I know? If you do, try it and see if your answer matches. If you don't, and only if you don't, do you then look at the question and try working backwards. So once you know the answer is, it's a good approach then to see, can I match it to the question and I understand it? If so, move on to the next one. So each question I've supplied has got the mark scheme following it. Okay, so for example, that's the second example I included. the answer is there at the bottom for you. Okay, so I wish you luck. I'm aware that most of you over the next few weeks will be assessed in some form. It's not the normal exams, but nonetheless, this is the last time I will formally have this opportunity to wish you luck over the next few weeks. Okay, but the main thing I can tell you, as I've tried getting over to you, just don't panic. Okay, chemistry looks like the most awful, massive topic, but it's honestly not that bad. Okay, so I will be present next week to answer your questions whilst Mr. Black presents the last session, but nonetheless, can I wish you luck? Okay, good evening.
Hiya. So I'll just let you know, I'll be looking at rates of reaction next week. So we're looking at how to measure rate and some of the calculations involved. All right, have a good evening, guys. Thanks, Ms. Stevens.